All right, 7 o'clock. Let's get started. This is going to be my last review with you because after the midterm, is a 1 week break and then we will see each other in school. All right, and for today's review, I actually will be going through almost all the lectures except for lecture 13, which is a dynamic programming. That is another difficult topics in a way. We will have both tutorial and recitation to help you to get through that. Okay, so no more review for next week, and I will see you next Saturday at 10 a.m. Or actually, it should be earlier. You should come earlier. We would allow you to enter around 9:50. Right, so you must judge yourself over the weekend. School buses may not so frequently, and you have to plan your time properly. The test will start on time. TA jobs, like you have seen, how TA helps you if you are interested in being a TA yourself for the next round, meaning next January to next June. You can tell your TA. Of course, our TA will make recommendation to me also, and through our face-to-face lessons in class, I will also see you. I will have some feel about how you are doing and so on. All right, but anyhow, you feel free to tell your TA if you are really interested in the job. All right, it does get some pay as well as it will get my recommendation letters for other purposes that you may have to apply for some overseas trip and so on. Okay, so for today, lecture 13, we'll skip that. For lecture 10, actually, it claims that you should know everything about Python by now. Of course, at least everything about Python for our purpose. For that, it also means that we are familiar with Python stuff, but you're not expected to apply all the libraries in Python, so they are plentiful. There are many of them actually. But you should, if you need to work with them, you will have times to study them and so on. For our midterm, you're not required to know any of those stuff. Same for the practical exam. We will not test you. You will not be allowed to use some of the libraries which may have ready-made solutions for our questions. So those will be excluded from our midterm or any other assessments. Okay, for number 10, the claims about you know everything about Python, but at least there are two other things that I should share with you. Let me just pull it up. This is about the map that you see quite a number of such a thing in our lecture, but we make all these things ourselves. So for map like this is actually with nothing in front. This is actually the system map. And when you reach here, then it is our own map function. So our own map function actually behave different from the map in the system, as some of you may have already found it. Okay, let's see what I mean by that. So in the case of a system map, actually you will get an object, you get an iterator, right? System is an iterator, meaning that you will get your answers when you get one by one. All right, so the first call to full x2, x2 is a map of 1, 2, 3. 1, 2, 3 is mapped to 1 square, 2 square, and 3 square. So you should get 149. All right, so for full x2, you should be getting 149. 149. Okay, at this moment that you have finished your map 149, actually everything in map is gone. All right, so the second time you call it, you actually get nothing. All right, end of second call. So this is a system map, which is an iterator. An iterator will give you the things one after another, and after that, no more. Okay. On the other hand, let's try another one here. Another thing here you can see. This map is actually an object, even though it gives you 149. If you take y equal to 149, yes. If you try to check whether 149 is the same as x2, which is the map, you will get negative. Okay, false. Of course, is false. All right, so now if we do our own map, in this case, our own map, it means that you override no longer using this map. We use our own map. When you do this thing, the same again, you actually get 149. All right, you get 149. All right, the next time when you call it, you again get 149. All right, it's because the way that we structure our map is such that we just it's just a tuple, and the tuple is always there. All right, so that's why in the last recitation you saw something about if you want the map object to be changed to the tuple, you have to explicitly make it into tuple. All right, so this is one point that you have to remember. Why I bring up map, it's also because I'm going to post in the forum. You write a more powerful map, more powerful than this guy. All right? Because this guy only handle tuple, whereas this map in the system, it handles all sort of, it can be list also. It can be more bizarre way of doing things, as you will see in the forum posting. All right, so I'll leave that in the forum posting. I encourage you to think about the solution, because the solution requires you to use things like the star in the argument. All right, which you learn in this lecture number 11, lecture 11. All right, so let me just continue with this one. This is the own map. I will post this code in the under the section of the review for you to take a quick closer look of it. All right, so in this case, this map of 149, it's indeed the same, okay? But they are still different because they are two different tuples, even though the values are the same, but y is not x2. All right. The next example I have here, it's about range. On the other hand, range is different from the map. So in this case, the range from 0 to 4, all right, 5 is excluded. So x2, it's 0, 1, 2, 3, 4, okay? And range is such that if you call it a second time, it still be there. All right, so it was the first time, the second time was there. Now, if you check whether they are the same, y equal to x2, y is this 0, 1, 2, 3, 4. Though this is the same as the tuple, but this is an object. So the two of them are not the same. So you get false. And of course, they can't be equal, then therefore it cannot be is. Right. On the other hand, there is this operator called iterator. You can x2 is actually 0 to 5. You will change this to operator. You can get this guy actually give you 0, 0, 1, 2, and so on. So next is you get a 0, then you get a 1. So I in the for loop. So I in the for loop. Now the iterator is the same as the original system map, that once you use it, it's gone. You get 2, 3, you get 4. And then now it's R is nothing. So when you try to print it, you get nothing. Okay, I will leave this code in the review section. All right, so that was lecture 10 that it claims you needed to know about Python is all there, except that there are lots of libraries available in Python. That's why Python is a kind of popular language, because of all those libraries ready-made to solve a lot of problems. Okay, but it's none of our concerns in this class. You're not supposed to really an expert in using those library. It doesn't help in this course. This course is about computational thinking. Okay, so you're okay? Give me a check. Okay, all right. So lecture 11, it's the more difficult lecture. This lecture has been there. It's narrated by Ben Leong, because I find it difficult to change the style, and also it's pretty comprehensive. What I needed to do is just to give you a review to reinforce your learning from those videos. All right, so I give you the gist of things, all the high level things. and then hopefully that helps you to study that the videos. All right, for today, I looked through the video again and I did some corrections in the video, which I cannot change because it's by him. There's some the code itself, it's not quite right. I changed the content Z on page 35 to just Z. And also I provided this new program, this one, dispatch on type, so that when you study this lecture, it's easier for you that you have all the three codes. These are actually the three types of three strategies that you can use to achieve generic operators. All right. So while you are studying this particular lecture, you have to read the code at the same time to help yourself. All right. So this is what I meant. All right. So in this particular lecture, actually, this lecture is difficult because at times it's confusing who you are actually. Well, who are you? Right? Actually, you are the application programmer. They are just like in the computer systems that I keep talking about. You have layer by layer of development. So if you are at this layer, you only see things on this layer and interfaces to the below layer, and you're not supposed to touch the below layer. That means that you cannot jump layers. All right. So in this case, it's saying that you are a programmer in this lecture, and whatever things that generic operator given to you, it's from such a thing called system programmer. All right, those people who manages or manage the systems, it's called the inside working of system, and they are trying to make things easier for us as an application programmer. All right. So that perspective has to be there so that when you read this lecture, you'll be slightly easier. All right. And not to say that it's easy because it's a lot of details are given there. So basically, what we are trying to do is still managing complexity as when you are allowed with multiple representations. Then how do you want to put the burden on the user to know that you have all these multiple representations, or you want to shield the user, which are these are people like us, from knowing that? And usually people want to hope that you can provide that. You as in the system programmer can provide that. Okay, so all in all, this is still managing complexity, which is one of the major theme in this whole course. All right, you know, CS is equal to algorithm plus data structure. Algorithm, it's a recipe. Data structure, it's actually ingredients. And what we are trying to do with all various kind of topics, various kind of techniques are trying to manage complexity. Okay, so in this case, this lecture is about managing complexity because we have multiple representations. All right, when you study this lecture, you will start it out with the Ben Leong has nicely put it that, you know, you have multiple representation. Then how you do we want to expose this to the end user, which are we are the developer? Right, here are two representation. Do you want to expose this directly to this guy? If you do that, then this will become complicated. You have to always remember which one am I using. Okay. On the other hand, you can shield this. You can avoid such a thing by providing the layer which is called a generic operation. All right, so the previous slide is this one with nothing. You are seeing this kind of stuff. And the next slide is you created this layer. All right, so how to create this layer? It is the main part of the discussion. Basically, there are three ways. The three ways are the message passing. If you look at the all right, it's a dispatch on type. All right, this is the first type, which is pretty straightforward, but kind of useless. And the data directed programming, this is the second type, And this is taking the opportunity to introduce to you the use of dictionary. All right. This is quite good already, but it's still not as innovative in a way like the message passing. All right. So this is like kind of like increasing the difficulties. But actually, this is not so difficult. It just embrace everything as object, as it just naturally blend into from lecture 11 to lecture 12, OOP. All right. And so let's go through each of these slightly. And you still need to take your time to study it yourself together with the codes. So first of all, there are actually two problems to resolve. All right. So the first problem is that, yeah, for example, if you have this kind of operation, okay, string one plus string two plus blah blah blah, okay, then this plus actually in the case of string it means concatenation. All right. On the other hand, if you have 10 plus 20 plus blah blah blah, this is actually our we commonly known as addition. All right. We know this very well. All right, but they are both the same symbol, plus and plus. Okay, then this plus semantically it's different from this plus, but our system allow us to kind of like freely use this this plus. We don't want to make it as plus subscript s, all right, as small script s. All right, in that case, it's like overdoing lah. So we want to be able to be as simple as possible. So in this case, this is the first problem that the generic operator has to resolve. When you see a generic operator, you must know which representation it has to go to. All right, so a plus in the case of rectangular, what must it do? In the case of polar, what must it do? So in our case is that a plus it's for the case of string versus the case for integer numbers or numbers. Okay, so the generic operator, this mechanism, this layer has to sort it out for us. And so whoever is at this layer, that's we are at this layer, need not know that the plus you have to go this way, the other plus for the string you have to go this way, the plus for the number you have to go the other way. All right, so this is the first problem that it has to resolve by the generic operator among all these three strategies that we talked about. And so in this lecture note, you see that at the end of each strategy, it asks the question whether these two are resolved or not. And on top of that, actually also the third question is about extendability, meaning that in future, if you have this plus for tuple, how do you do? Okay, then it will be different for string and so on. So this kind of expansion, what is the impact to the strategy that you employ? And so all these judging all this, then you decide on a particular strategy, or you, in this case, is system programmer. Okay. And the next question is that the name issue. As you study this lecture, you see that there are two versions of I believe this lady. This is Ben is the lecturer. The lady is Alicia's Ben's version. All right, and then Elsa's version. All right, so you see that the name, in this case, before you have the generic, they all live in their own space. They don't care about each other. But when it comes to when using the generic, they're all in the same space, then there's issue about the name. You can no longer use the same as make from real imagine. You have to say underscore rectangle, underscore rectangle, underscore rectangle, underscore rectangle. And same for this other version, you have to underscore polar, underscore polar. So this is not so helpful for the programmer. In this case, actually the programmer, us, would have to know explicitly this kind of different in names. All right, so this is no good. for the first strategy. And the strategy, we have to shield this away from the user. So let me just call up the first strategy. All right, the first strategy is called dispatching on type. So the code looks like this. All right, so the code, you can download it and run it yourself. So I have example at the end. Using dispatch on type, I created two complex number, ZZ1 and ZZ2, using the polar representation. And then I also created ZZ2, ZZWW2 in the rectangular representation. Now, this particular first type of strategy, it's actually tagging. Your generation is very familiar with tagging. You tag a picture with somebody's name there. You tag a picture with a certain event and so on. It's the same here. So basically, the representation is such that the number, the ZZ1, it's tagged with polar, okay, and ZZ2 is tagged with rectangular. This is the actual number. This is the actual number, actual complex number, and they are tagged with this and this. WW1 is the same, and WW2 is also tagged. All right, so this first strategy is tagging. All right, the tagging can kind of like help in some way. It able to do now. You have to. The strategy for tagging is that you are going to use a lot of if statements. Okay, you need to use if statement. For example, you see that to find out the real part of Z, first of all, you have to check, is this Z, which is a complex number, is it rectangular representation? If it is rectangular, then you take the issue, the name from rectangular, right? The real part from rectangular. If it is polar, then you take it from polar, all right? And if there's none of this, then there's exception, right? Something is wrong. Similarly for imaginary part and so on. So all this become a generic operators. This generic operator is then shielding you away from having to know which is which. You always call the same function. In this case, I call the same function. I don't care what it is, I always print. I want the angle, I just print the angle. I want the magnitude, I print the, so angle is the same as this angle, whichever representation. Now, if you do addition, it's then at the back, I also do some example for you to see if you're adding two of the same representation, different representation, different representation, different representation, different representation, same representation. Whatever representation you use, you always get the same answer. All right, adding two complex number, you always get the same answer. Okay, but the tricky thing here is that the output is only one type of representation. It has chosen it to be rectangular. All right, so this is strategy number one. Strategy number one is dispatching on type. Basically, it's tagging. All right, is the tagging approach, and the tagging approach requires you to then use a lot of if statement to check which is which. Okay, so this is strategy number one. And strategy number two is as I told you just now, is taking the opportunity to show you how to use dictionary. All right, so you use a dictionary to store the reference. Basically, now this particular strategy, as you read about it, you will know that it actually can resolve the name issue in the sense that all the things are stored inside the dictionary. You don't worry about which is which, right? You can use the same name, no issue. And because they are in the different, once you see this, let me just call it out. This dispatch, so I'm done with this. The next one is data directed approach. This is the number two. All right, this is the dictionary. So you have a thing here called install the package. Basically, This installation is to put things into the dictionary, all right, so that you can then, whenever you encounter a operator real part, what you want to do, you just apply generic the real part to Z, okay? And this real part will then refer to the table to find out which function you should use. The interesting thing in Python is that you can store a function also as in the table. So this is a function name, this is a function name, this is a function name. This function name is for the polar coordinate under alpha, and then this real part is under then, and these are just so you see the real part is the real part here, and there's also a real part here. So there's no issue with using the same names now, all right, in this particular approach, because everything is now cast or mapped or put into the table. All right, so here are the operation. If you want this operation, I just simply say apply generic. Apply generic is just to take it out and then get the operation and then apply on it. All right. So if you want imaginary part, I will just map it and I will just use it, apply on this guy. So you needed these two functions, and otherwise when you run this, it will give you the same thing. Okay, you will, whichever it is, you still get the same thing. And for this one, I didn't give you the addition. You can always add it to the addition into it. Okay. So this is strategy number 2. It uses a dictionary to store the references. And this is a part enabled by Python because you are allowed to put the function name into a table. And then the table lookup to use which operator type. This is very organized and solve the name issue. And of course, it also solved the other third problem that I didn't mention, that is the expandability. If you have a new type, you can always add another row into the another column into the table. There's a polar, there's a rectangular, maybe there is a TTS, and then there will be another column. All right, so you check it out, this data programming Python code to see this. Okay, so this is the second one. The third one is equally interesting. You're actually seeing this thing very often in the coming exercises in the recitations and tutorial. It looks like this. So this is a prelude to discuss about object-oriented. So this is actually the how a rectangular is represented, and all are embraced or encapsulated within here. So you see that when you're making a real part, you make a real helper, you are doing this, right? And you can also make it from angle to if you run this thing, you see that they are the same. In the sense that you will get, I set them to be the same. 3, 4 is the X is 3, Y is 4, 5 is the magnitude, and this is the angle. So these two are the same complex number, but they are in two different representations. And in this case, there is no name issue, so the name is the same. You just have to call him by the real part, or if you want the real part, you call him by the real part, the imaginary part, you call him by imaginary, and so on. So this is actually the simplest and pretty powerful. We see this thing a few times. Actually, in one of the years PE, I actually put a question like this there. I can try it out. All right, so this is actually called message passing. So this is actually close to the object-oriented programming. In object-oriented programming, there are 3 words that you always have to remember. These are the encapsulation, inheritance, and polymorphism. We will get to them in lecture 12. And we will criticize Python in due course that it fails to provide all these things. That's why we also have lecture 14 and 15 on Java, which they are the one that Java is the one that obey the object-oriented principle. In this case, we mean encapsulation, inheritance, and polymorphism. Okay. So here, actually, this is a point where I actually hold on to my last example last week, and this is to talk about here. All right. So this is another third example that about in real life analogy. Okay. Only Bruce posted something there. Okay. But I anyhow hope that you observe this in due course in this journey that you have with actually if you are choosing this line of work, and then you should see many more examples. Okay, in real life, my example here now is to talk about CS1010X. You, me, and my TAs and so on are put together in this called the marketplace. Okay, this marketplace is our class. Okay, we are now in this class and we talk. I talk to you, I ask you question, you ask me questions, TA asks you question, you ask TA question, you do some assignment and TA mark it and so on. Okay. And our objective here is to learn computational thinking. All right. Then we are not talking about any other thing. Now, when you take this example into object-oriented programming, let me do bit by bit. In Python or in object-oriented programming, what you're seeing, of course, you're going to hear this over again in my face-to-face recitation. But anyhow, let me just say it, at least here, it may take you a while to realize that in computation, actually, all right, like what we are learning together in 1010X, it's a marketplace. All right. A marketplace, it's in the case of Java, it's static void main function in Java. All right. In the marketplace here, it's putting the various objects together. All right, objects. So like this case, this is an object definition. Okay, and you want the object, you make that and assign it to this guy. So ZZ is now an object, whereas this is the template to make an object. So this is the object definition. So this line here is to say that we initiated or instantiated an object called ZZ. That basically we are born by our mother, all right? And we born and then we are now an individual. Okay, so this object is there. And then this is another object. Okay, so we put objects together. All these objects are, in this case, in our case of our marketplace, our class, all the objects are the same thing so far, as if the same thing. Meaning that you, me are human being. The TAs are human being, but also we also use video. Okay, those are not. There's another object. So we learn from videos, we learn from PPT, we learn from missions and so on. All right. So all these are various kind of objects. So you have 16 missions. You have 16 missions objects. All right. So we are put together to interact. And how do we interact? We actually passing information around. So this case, all right, so angle ZZ. When you say this, you are actually calling this function. All right. When you're calling this function, you are giving this object, all right, which is the parameter here, this message called angle. All right. So when this object receives this message angle, he knows that this object is, in our case, ZZ, is a rectangular representation. You will check through if operator blah 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 hits here. You will calculate this. Okay, so that's why this is the object. This object is receiving this message, and this message passed to him. He knows what to do because he himself knows which object he is, which type of object he is. He is born from here. So he will use this version. All right, so maybe I can prove to you let me just comment out this. These are all the W, right? We only look at the Z. So I'm going to put in a print statement here. Okay. Okay, let's see this. All right, so these are the Z is nothing will print the angle and magnitude. Angle is UU, magnitude is SS. You see, UU and SS. Now, it knows that it has to go to here instead of here. Here also got the message angle. All right, but it doesn't come here. Why? Because this object is rectangular in representation. You give me this message, I know where to go to find my angle. This will be the way to find my angle and so on. All right, so this is passing a message. Passing message is here. Okay, so in this marketplace, things can happen like this. An object work on itself. For example, you study on your own. Okay, you work on your mission yourself. Okay, and an object work on itself together with other object in the class. So, for example, you posting in the forum or you talk to your friends about this particular exercise or this mission, and then you're working with each other. Right? So this object, human, you work with another him. Okay. And then object can also work with object of your in this same class. So for example, you're viewing a video. The video is another object. Video for lecture 11, all right, that's an object. And you may also work with your pen and pencil because you want to take notes and so on, or the PPT at the same time, okay? So, and a marketplace is where all these things are put together and work together. And in Python, in Java's case, the marketplace is a function which is it doesn't belongs to anybody. In fact, you can put it anywhere but it just happened to put it in the particular class. But this static void main function can go anywhere, any of the file. Right? If you are already at the Java video. Okay, so but of course, if object work on itself, you're putting into your own class, and then object work with other object of the same class, you're also in the same class. Object work with other people, and you can also have. You will see this class called food and vending machine in my recitation number 9, I think, or somewhere. Then we will see that actually you can work with vending machine, have food, and the food has so vending machine has food. That food is another class. Vending machine is another class. All right. So these are the various way of interactions, and the kind of interactions. Even yourself working on yourself is also passing on information. All right. This is how the computation come about. All right. And because of all these things, to protect the kind of like the making sure that all these things about the three keywords about object-oriented programming. The where are they? Let's see. Uh, Here, encapsulation, inheritance, and polymorphism. All right. So we all have to have accessors and mutator. All right. So basically, outside people cannot anyhow change you. Only you can change yourself. So for example, when a message get to you, you decide what to do. But you decide whether you want to change yourself or not. And all this protection can be built into the system, and so that the code become maintainable, become much easier to avoid some of these silly bugs that usually people commit. Okay, so you provided with accessor, mutator. So programs tend to look much longer, but it's for the good of other people to behave. Because if you don't protect it, anyhow, people allow you to change things, which is the case of a Python, then you are not going to achieve encapsulation, inheritance, and polymorphism. And then you are just like using OOP for the sake of using OOP, but you are not taking the advantage of having the OOP. All right. So in the case of Python, OOP requires actually discipline. Yeah, it doesn't provide you for as it's. You have to behave. All right. Basically, it is something which you can break, but hopefully you don't if you want to have to be a disciplined programmer. Okay, so I pretty much done with this. All these weeks that you are with me, hopefully you know that I'm talking about all these things. All right, CS is this, algorithm is this. Lots of things in computer science got to do with real life. You are actually managing complexity for problem solving. Any question? Yeah, okay. Give me a check, then I go on to spend 5 more minutes on the midterm. Okay. First of all, midterm all this assessment is a necessary evil. We needed them to help you to learn, but don't be too stressed out by all this kind of stuff. You will see the last line here is that sleep well the day before, and just be yourself. Okay. Yeah, you need that. Sleep well on the day and wake up early to come to to school, to the venue to by 9:50. Okay. Now, to prepare you a little bit, the midterm is 40 marks. The front page is already in the lesson plan. It's a 2-hour test. The sitting arrangement is also given. Okay. And to help you to zoom down what you should see, and of course, my style has changed a little bit as in the last few years, it tend to be 4 or 5 questions. This year, there are only 3 questions. You can avoid, you can, it's not that I want you to, of course, more exercise help you. What I want to tell you is that only these papers are done by me. Other years, they are not my responsibility. We don't have solutions for them. If you cannot find them, you will have to use a post in the forum to help yourself and each other. All right. For me, these are the years that the paper was set by me. All right, by myself. And for example, 2024, I was teaching it, but I didn't set the paper. So that's not my style. Okay. My style you can find in 2020, 2021, 22, 23, 25. Okay. And you should also see if you want the final exam. Okay. Because final exam covered some part of your earlier in the midterm also. But of course, the final exam will be more comprehensive with many more topics that included. All right. Question 1 has A, B, C, D, E, F, G, H, 8 parts. Yeah, 8 parts. How come 9 parts? A, B, C, D, E, F, G, H, 8 parts. 28 mark. Okay. I may have missed something. 28 marks, which is quite a big proportion of the 40 marks. It's a tracing. Basically, you are asked with a question and you are supposed to give the answers. So as in this case, it's very hard for us, as stated in the question, to give you partial credit. But of course, if you want, you can always show your working, but make sure that your working is on the side. All right. And but we cannot promise you that we will look at that. We have to check mainly the answer. If there is if there is any issues, you can always contest in the marking after you got it back during depending on when I want to release it. If there is no re-midterm, I will release it soon. If there is a re-midterm, I will have to delay until the re-midterm is finished. Okay. Basically, you are supposed to do tracing. all sort of tracing. By now, you should know that tracing, you require to use some kind of tables or some kind of diagrams or whatever that you are comfortable with. All right, there was a question about whether stack is included or not. It doesn't really matter to me because you have seen a queue. Stack, to me, it's just another application. But anyhow, I don't think you should contest that. I mean, stack, you see in a game, lecture 8 or 9 of 10. Yeah, okay. Now, question 2, it's a short question, 6 marks. There are 3 parts to it. I don't think I should tell you what it is, which topic it is, because it will give out too much. Question 3 is yet another 2 parts. It's also 6 marks. And so that make up to be 40 marks. 12 plus 28, 40. Okay, we have 5 minutes. You can ask question. All right, so I just see it. Ask me, will stacks, queues, and set be tested for midterm? My answer is yes. All right, at least set, you see it in the listing of lecture 8. Queue, you saw it last week. And I also in the posting in the forum, I believe. Was it this one? No. Oh, it was in the recitation. Yeah, yeah. All right, this was kind of interesting. I study 2 versions from you guys. I make slight changes and I make this so that it amortized to be correct. And thank you to uh, Tian Tai that I actually the explanation is good enough for me. Am I allowed to submit my rough paper together with the answer booklet if I have done working on it? No, no, we don't take other than whatever you wrote down there. No, no, no. You should be confident in transposing your answers to the transcript. Okay, we only take your transcript. Sorry, your the test paper. You will be writing in the booklet directly. No separate answer booklet. Okay, sorry. Hila, I cannot take that. Anymore? You can ask directly by shouting it out. No?
Hi, Prof.
Yes.
For naturally recursive problems, example traversing a tree, if we are asked to use iteration, do we have to use a pure iterative method such as recreating the recursive stack using a list, or can we do a bit of recursive inside our iteration?
Oh, uh, okay. Whether you can or you cannot do, it all will be in the paper itself. If the paper doesn't tell you cannot, that means you can.
Okay.
Okay. And you always, if you think that the language is not clear, put down your assumption. That we will consider.
Okay, thank
Ah,
you.
Meaning that you have, if, in case of any benefit of the doubt, whatever, you want to play safe, you want to write a little bit more. Actually, as you can see, only these 2 questions you can play safe. This one is all straightforward answers with print statement. Okay, only question 2 and 3 then. What if we run out of space in answer booklet? Hey, the answer booklet won't run out of space. We only print on 1 page. The back page is empty. Hey, why we decide this way? It's also making it we have only the limited time to finish the marking. So we want, hopefully, you don't want to torture us with long answers. But you will torture us in this too. So, especially this one. So yes, but don't torture us in here. This one is pretty straightforward answers. Okay, here and here are the only two places. So I'm pretty sure you have enough space. How comprehensive must our explanation of time and space component be to get full credit? Oh, yeah. So this has to be comprehensive enough. Yes. As to how it is, okay, here's how the calculation. There are 40 minutes, right? 40 minutes for 2 hours. Well, 2 hours means 120 minutes. 120 minutes are giving you 40 marks. So each mark will take you 3 minutes. So if you see 6 mark, this means at least 6 is 18 minutes. This one is 18 minutes. All right. So how comprehensive? Also, we have provided enough space for you. If you can check all the past paper, enough space are allocated. A few lines means you just write a few lines should be enough. But anyway, the time is also a way to judge. On the other hand, this question, 28 marks, some are easy, some are difficult. So you yourself have to judge it. Okay. But this one, 6 mark, you can tell it's about 18 minutes. This one, 6 mark, you can tell about 18 minutes. Okay. All right, Joel, is that okay for you? Okay, any more? It's now
Do we need
50.
mathematical proof for the time and space complexity?
Mathematical proof. Time and space is mathematical. Yeah. We are not wishy-washy type to on our answer one. If you bluff your way, I know. Okay, so at least there's some truth to it. We are pretty. I mean, our math are also pretty simple, right? 1 + 2 + 3, that type. Or whatever, or 1 plus whatever plus A times R, the arithmetic versus and also uh, a geometric progression. Okay. I think that should be it. Don't be too stressed out. Sleep well. And I think I need to pass to Junjie already. Junjie, are you there?
Yes, hi.
Okay, great. Uh, Take care and happy Hari Raya.
Prof,
Uh,
sorry, wait. Can we use pencil for the exam?
Of course you can. We love you to use pencil because you can erase and make it clear. I don't like pen because once you use pen, you when you need to do corrections anyhow one. Pencil is welcome. Anyway, we will not. You will get back your paper, so we cannot erase anything you write. Okay, so pencil is welcome. Okay, Junjie, I pass to you as the host. Hold on, You have it?
Yep.
Okay, I leave now. Bye bye.
Bye. Right, guys, I'll start at 8, but hold on. Let me share my screen first. Right, hi. So, I'm not sure if you all actually look at the PDFs when you all do the tutorials, but there are some questions where you have to draw stuff and it doesn't show up in the cosmology tutorial page. So, you should look at the PDF because there might be some extra questions. So, I will show you. Question 1 is a question that requires you to draw box and pointer diagrams. So if you haven't drawn them yet, please draw them now while we're waiting until 8, because I'll ask you guys to show me your diagrams and I'll tell you if you all make any mistakes. So it's very good to get some practice, because box and pointer diagrams will come out in exams. I mean, it can come out in exams. All right, hi everybody. It's 8 p.m. I'll start the tutorial. Today's tutorial is tutorial 5, working with sequences. So like I said just now, I hope you all have tried question 1 and drawn box and pointer diagrams. So box and pointer diagrams is a very important thing you should know how to draw, as it can come out in exams. So can you guys send me like pictures of the box and pointer diagrams you drew for part A, B, and C for question 1? I'll show you guys how to draw later. And also for those that want to try something a bit more practical, that following an example that may actually come out for exam. So usually in exams, right, there will be like ADT questions where you implement the ADT according to some example, right? So here is a products and cart ADT example. So we have a product ADT, which is basically just a tuple of a product name and price. And we have a cart ADT, which is the name of the cart and a list of all the products that are inside the cart. So if the question would be an ADT on this, like some sub questions that will follow up is like write a function that returns the price of the total price of the cart, or like add a product to the cart, remove a product from the cart, these kind of things. But today we'll focus on just drawing the box and pointer. So if you all have finished everything above, you want to, while you're waiting for me to go through the other questions, you can try this one. Draw the box and pointer diagram representing this card. Okay, I'll go through the above questions first. Let's see. Can you see my screen? Can you see Jun Hang's question? Can you all give a thumbs up? All right. So the first question is A, we have a tuple like so. And Jun Hang's solution, okay, so it's a tuple with 3 elements. The main tuple, the outermost tuple, has 3 elements. It points to here, here, and here. So let's see. The first element is a tuple with 1, 2, and a tuple with 3. So let's get a pen. This part is correct. Correct. Second part is 1 tuple. The second element of the outermost tuple is another tuple, 4 and 5. So this is correct. Lastly, we have a tuple with 6 and 7. Is correct. Yep, so good job. Good job, Jin Han. Okay, next, let's go through part B. Okay, I'll look at someone else's example for part 2. Okay, so, okay, Yi He Chiu's answer for question 2 is, let's see. All right, so let's say the name of the tuple is B. So we'll have B, the variable name, point to the main tuple. And usually when we write in the box, you can do an arrow that points out to just one, or you can put it in the box. Most importantly, when you point out to other tuples, you need it to be like that. So you can draw it like this. 3. And representing other tuples. Yeah, correct. So let's see. So when you're drawing box and pointer diagrams from a tuple, you should first look for the outermost tuple, how many elements are there. So the outermost layer has 2 elements. So this is correct, 2 layers. Within this tuple, how many elements are there? That's 1, 2, 3. So 1, 2, 3 is correct. And lastly, in this innermost tuple, there is 1 element, which is correct. And that's 1 tuple. So Yi He Chiu's answer is correct for part B. Okay, let's look at your answers for part C. Okay. Okay, Isaac, I think yours didn't copy properly. Oh wait, it does. Oh, I see what you're doing. Let's look at Julius's answer. See. All right. For box and pointer diagrams, you don't need to label it's a tuple. Whether it's a list or a tuple, it doesn't matter. We're just representing them with box and pointers. So yeah, for part 3, let me show you the question. We are going through part 3 right now. So for this, first element, first look in the outside, how many elements are there? For the outermost layer, there's 1, and there's another tuple over here. So it's correct, and this part is correct. Look into this inner tuple. There is 1 element and another element, 2 elements. So this is correct. This part correct. Pointing up to an inner tuple. The inner tuple has 3 and a 4-5 tuple. So 3 and a 4-5 tuple, correct. So yes, Julius, your answer will be marked correct. Just you don't need to label the tuple. And all right, for this, this is typically where you will actually draw box and pointer diagrams, probably for ADT question, because this is rather simple, just drawing a box and pointer diagram based on a tuple. But usually there might be some questions where after you implement an ADT, they'll give you 1 instance of an ADT, 1 instance of a card, and it show you how it was made, and then you'll be tasked to draw the box and pointer diagram for that. So this one is a bit more complicated. It has strings and floats, but the structure is the same. So, can anybody try drawing the box and pointer diagram for this question? All right, okay, wait. So while y'all try this, okay, I have another question here for part A and B. Somebody asked me, could you explain the difference between box and pointer diagram for 4 tuple and 4? Okay. Okay, so I had a question coming. Can you explain the difference between a box and pointer diagram for 4, comma, and 4? So the thing about this in Python is, this is the syntax for creating a tuple with 1 element, right? But if you do this actually does not create a tuple. 4 with just the brackets. This actually just simplifies to 4. So 4 is equivalent to just 4. So there is no box and pointer diagram for this because it's not a data structure. It's just integer 4. If you do want to create a tuple with 1 element, you have to write in this notation. So that tuple will actually be just a box pointing to 4. And this is simply an integer, which can't really draw a box and pointer for that because there's nothing to contain. I mean, there's no container for 4. All right. Has anybody tried this question? This is an extra question I came up with. All right, in the meantime, let's go through some of your other questions. Okay, for this Godwin's example, you need to show the arrow because like you don't want it to be ambiguous, like what if you meant this will be a completely different tuple, right? This will be a completely different meaning. So you have to show the pointer. That's why it's called box and pointer diagram. You need to show the arrows. Like where is the main tuple, where is the outermost tuple, and what are the inner tuples. So you must show the arrow. It's good to also like point the arrow out like that. Okay, this would be marked wrong, but it's good to learn, like because box and pointer diagrams has a high likelihood of coming out in your theory exams, so you must know how to draw. Let's look at this one. All right, so you labeled the indices. That's not necessary, so no need to do that. This is correct. Yeah, you use the arrow pointing, which is good. No need to show indices. This will be correct. Okay, Zizeng has answered my extra question. Okay, Jinji's card. Yes, this will be correct. So what you typically do is, okay, so the name of the variable is card. Card is the name of the variable, so it should point to the main tuple. Don't get it confused with the card name. It's just part of the data structure. You see, a card is the name of the variable, and the card ADT itself keeps track of the card's name. So this is what we would do. So card, the variable name will point to the main tuple. And yes, over here is the string, Junjie's card. And this is the first element, right? This is the name of the card. And this is the second element, correct? We'll have a list of the actual products. So a list will be represented by another box. So whether it's a tuple or list, we use box to represent it. And each of the products over here, each of these are individual tuples. So they should all be in a box. So you can actually point them out and write milk. And over here, point them out, it's like $2.50. It's a bread. It's $1.50, $1.20. Yeah. And eggs. Yeah. You should show the quotation marks to show that it's a string. Because like over here, this is a variable name, so that's why it's not in quotation marks. Let's see. Let's try. Okay, if you want to see the answer, you can relook at the recording. Okay, let's see. Over here, yes, this is correct. It's correct. If the question actually provided a variable name for it, like let's say var3, then you have to point it to the box. So like if this was, let's say, tab2, then you just point it to the box. So this is the variable the tuple is saved in. So yes, correct. Yep, this is the way. No need to draw the little dot inside. You can just draw an arrow. All right, we have Yi He Chu's attempt. So okay, no, this is incorrect. You should not don't do this. Don't show this. Because we are actually just showing the structure of the data structure, right? You just point it straight at what you're referring to. So this all the way, just come and point this. If you do it like this, then you'll be correct. Yep, otherwise this is correct. Point it straight at the data structure. So what Zhizhen Huang did is correct, just that you should also do this. Right, everybody got it? For box and pointer diagram, this is likely to come out. I mean, I wouldn't say it will come out. I'm just saying that for past exams, it has come out and you need to know it. So let's see, what if it's like a dictionary key and we separate the key? Okay, we don't draw box and pointer diagrams for dictionaries. So far we've only tested our box and pointer diagrams for lists and tuples. So that's all you need for the midterm so far. Okay, question 2. Let's move on to question 2. Write expressions using index notation that will return the value 1 when the identifier tup is bound to the following value. So when tup is equal to this value, I will just choose your names. Okay, so Yi He Chu, can you give me an expression? Can you give me an expression? There are actually like two different ways, but there's actually a lot of different ways. But as long as the expression can return 1, it's good. So Yi He Chu, can you give me an expression for question 2? Okay, just write it in the chat. All right, let's see. Okay. Yes, correct. All right. Now all right, Debansha, you try also. Debansha, can you give me another expression that will get the same result using negative indices? Instead of this way, we have another way. Snooze. Okay, Debansha, try using negative indices. See? And yes, correct. So negative indices are index from the right. So look at this tuple. There is 1 element, 2 element, 3 element, 4 element. So it's 4 elements. To get the last element, you can either use the index 3, because remember tuples in Python are 0 index. So 0, 1, 2, 3. You use 3 to get the last element, or use -1. Alternative also gets the last element. And once you have the last element, which is a tuple, you indice that again. So you can chain them, you can chain the indices to get the second element within this tuple. So you can either use 1 as the index or -1. -1 works too. So yes. Okay, now part 2, let's have Chen He Lim. Can you write in the chat your expression to get 1 out of this tuple? And Zheng Yuan Dong, can you write another expression using negative indices? Okay, so Chen He use positive indices and Zheng Yuan use negative indices. This is the part. Hi Chen He, Zheng Yuan, are you all there?
Yep.
Yes, okay. I should already just write the answer in the chat. Write your expression. Okay, while you're doing that, Ray Yang, you will do expression 1 for this part of the question, and James the Jun Tan, you do expression 2. So expression 2 is with negative indices. Okay, Chen He Lim, are you there?
Wait, so I can say again the expression 1 and 2.
Okay, Ray Yang, you're doing expression 1 with positive indices for this question. James the Jun Tan, you're doing expression 2. Okay. Chen He Lim, are you there? Hi, Chen He Lim. And never mind, Zheng Yan Dong, are you there? Are you done?
Wait, am I positive or negative? Wait.
Ray Yang, you're positive.
Eh?
Oh, I just realized another person with a very similar name. Oh, Ray Ang and Ray Yang. Oh, okay, now both of you answer the same question. You are correct. Yes, this will return 1. So over here for this part of the question, look at the tuple, count how many elements are there in the outermost tuple. So there's 1, 2, 3, 4. So look very carefully at the outermost layer, how many elements are there and whether they are tuples or not. So you notice 1 is in the last element. So you either index it by 3. Firstly, you can index it by 3 to get the 4th element. Now notice this is a tuple. To get 1, you need to go in to the 2nd element, which is also a tuple. And you have to index that by 1 again to get the 2nd element. And then notice that what you've gotten is a tuple. So if you want to get a 1, you have to index it by 0 to get it. Okay. Now, and James the Juntan, your answer was this. So let's see. Yes, this is correct. So notice the outermost has 4 elements, but you can just use -1 to index to the last element. And then once you got that, once you're at here, this will return this tuple, right? So you need to get the last element of that tuple, which is this. And you index into this tuple with -1, you get this. And then you have to index it again with -1 to get the last element in this 1 element tuple. Index it again to get 1. All right, let's see. So Nian Dong, okay, you have answered -1. Yes, correct. So that's how you get -1 with, this is how you get 1 with negative indices. Okay, Chen He Lim never got back to me, so I'll just show the answer. So this is a simple tuple with 1, 2, 3, 4 elements. So to get the 4th element, you simply index it with 3. So this will also get 1. Okay, so notice over here, this is a trick. So let's say they ask you to get 7. So this actually simplifies to just 7. So this is the same thing. Because as you know, for Python, the tuple notation, if you use brackets only for 1 element, you have to add a comma to make it a 1 element tuple. If you don't, this is just a mathematical operation for simplification to put parentheses to tell Python which order to do your mathematical operations in. So Python reserves that syntax for mathematical operations. So if you want to specifically get a 1 element tuple, you must use a comma. Else it will not be a tuple. All right, let's move on. Okay, so let's have Bruce. Let's do this with positive indices and have AJ Kartikeyan do with negative indices for this part of the question. You guys can also practice drawing box and pointer diagrams for these tuples. It also makes it easier to like visualize how to indice into it to get specific elements. Right? Okay, Bruce's answer is this. I don't know what's going on. Tuple index out of range. Okay, so this is wrong. So let's see why. So this tuple has 1, 2, 3 elements. So I think you may have misread this tuple. So this tuple actually only has 3 elements. So this is the 2nd element. And since you indexed it by 3, so Python will throw an index error because there is no 4th element. So an index of 3 tries to get the 4th element of this tuple, but there is no such element. So that's why we get an index error. So let's see. So what we should have done is we need to index into the 3rd element. So let's see what you do. Index into the 3rd element. That will return a tuple with a tuple inside. So you index that by 0 to return the 1st element, which is another tuple. So to get the 1 inside it, you need index by 0 again to get the 1. Yes, and this returns 1. Okay, now AJ's answer. Yes, also returns 1. So very simply, -1, this part returns this last element. -1 goes in to get another tuple, and -1 goes into that last tuple to get the one that's inside. Yes, so you should understand. I can mix and match with Bruce's answer. Yes, you can mix and match. You can use negative indices or positive indices if they get the same thing. So this question just asks for any expression to get 1. All right. So question 3, let's move on. Write a Python function called evenRank that takes in a tuple as its only argument, so only one argument, and returns a tuple containing all the elements of even rank only. So every second element from the left. So let's have your answers. Let's see. All right, so let's look at a simple iterative solution first. Okay, so Yi He Chu, all right, can you briefly go through your answer and also talk about the time and space complexity?
I don't know how this is.
Hi.
So this is like solution. It's like so it just loops through every single element in the tuple, and if it's even, you will just add it to a list. Then after that, return the list of even elements.
Yep. Okay, so what's the time and space complexity?
The time should be ON because I loop through every element. Then
And space?
space is 1 because I don't use any extra space. I
Okay,
think.
so your explanation is correct. The time is correct, but space is not correct. So notice that usually when we ask for extra space, if you create a new data
I use a
structure,
list. Yeah,
yeah,
so
if you
I
create a
need
new
the one
data structure,
space.
another list, and you add to that, so this will be extra space. So this space is the input. This is like extra space that you are using, and you are adding roughly n half elements, right? So that will simplify to ON. Okay, so take note of that. Okay, let's look at a simple recursive solution. Did anybody provide recursive solution? Okay, I don't see any so far. Can somebody write a recursive solution? Okay, wait, let's see. Yes, okay, Curtis has a recursive solution. Okay, so Curtis, can you go through this and answer the time and space?
I think the time should be O of n, and the space should also be O of n. Yes, O of n.
All right, it's n and n. Yes, that's correct. So can you explain why? So like what you actually write in the exam?
The time is O of n because the number of times that it actually loops through is actually n over 2 times. But since the half is not there in the big O notation, it just simplifies to O of n. So the same for space. Yeah.
Okay, but you should use the actual explanation that you give an exam.
Okay, so for the space as well, because it only takes out every second character in the tuple, so therefore the space that is required is actually n over 2. And then again, because it's big O notation, you simplify and remove the half, so it's just over n for space.
Yeah, I was looking for that is the number of a recursive call, the size of the recursive call stack, yes, because it's a simple recursive solution. So the reason why we use that much space is because of the recursive call stack. And that what you said just now was the explanation for time. As in like, that's because that's how many steps it took. It contrasts with something like an iterative solution, which may have, let's say, n steps, but use O1 space. Yeah. But here we use ON space because we are keeping track of another thing. But take note of like what to write in exams. When we actually answer time and space complexity questions, we need to provide a brief explanation as to why. Okay, I saw somebody had a slicing answer. Okay, Ashmit, can you explain your solution? Briefly go through it and also talk about the time and space.
Mine is going to be just it's just basic slicing. So and then you're returning the new tuple. I think the time complexity for this will be O of n, because slicing takes O of n as well, and making a new tuple also is O of n. So the total time complexity should be O of n simplified. And
all right, thanks.
Space should also be O of n.
Yep. All right, sorry, I had my screen paused just now. So just now we went through a simple iterative solution which made use of a loop, and we also looked so the recursive solution is the typical one that we usually show in lectures. Make sure you understand the differences between the explanations for time and space complexity. Now back to the slicing example. So this uses a basic slicing, which is we go from the second element until the very end. So over here, we don't write anything for the end. That will just mean we want all the elements up to the end. And we input step is with 2. So every other element. So yes, tuple slicing, string slicing, list slicing, everything like that takes O(n) time according to the length of the input tuple. And it's also O(n) space because what slicing does is it creates a new tuple. So what you return here is a new tuple. Obviously, it's a new tuple because like tuples are immutable, right? But it goes the same with lists. So even if, let's say, this was the input list, let's say like that, we are still creating a new list. We are not mutating this list. This notation creates a new list that is being returned. Same thing for string and tuple. All right. So is there any person who did using comprehension? Never mind. I'll try to look for an example using comprehension. Right, over here. This is an example using comprehension. So comprehension is just a notation. This is the actual comprehension part. So what we do here is actually a syntax called comprehension. An expression for I in range if this. So this is the structure of comprehension syntax. So over here is the expression for the elements you want. Each element in this iterable will be this expression. Over here you have a for loop thing where you go from I in range this. So this will return an iterable of all the indices that you use. And this is the expression that keeps only the stuff you want. So only when I is odd, you will add these into your iterable. So what you return here is actually not a tuple, it's actually an iterable. So you have to wrap it in tuple to convert that into a tuple. So this is just this is called comprehension syntax. And when we force it to be a tuple, we call it tuple comprehension. It's also possible to use like list comprehension and all stuff. Wait, which lecture is this called? Okay, if it's not explicitly taught during lecture, it's just like something that we show you. Some other students also will just like throw out this syntax. So this is Python syntax that you could use, but you don't have to understand it because it's not taught. Just that I've seen some people answer like that. And if you were to seek like external help from somewhere, I don't know, this might actually come out because it looks elegant, but I just need to make sure that you all understand what this means. Yeah. So this same thing is very similar to slicing. This creates a new iterable, which takes space. So it's O(n). And time, it runs the same number of steps, n divided by 2, so simplifies to O(n). Yeah. So understand how to do it iteratively, recursively, and with slicing. And this will be good to know. All right, so let's move on to question 4. Write a function called odd-even sums that takes in one tuple as its only argument and returns a tuple of 2 elements. The first is the sum of all odd ranked numbers, and the second element is the sum of all even ranked numbers. So you could use the function you implemented up here as a helper function. So let's see your answers for odd-even sums. There are many ways to do this. Okay, let's see, we have slicing answers. Okay, we have a use of accumulate. That's very good. So let's see, I'll just add that in. You notice all these problems that we've looked through, we could actually use like lecture taught functions like accumulate. So in exams, like they will just give you accumulate, put it on the outside, and you're able to call that in your answers, or like you'll be forced to for some questions. So you need to understand how to be able to apply accumulate, apply fold to sum to solve these kind of questions. So all these are these are your grounded foundations on how to implement solutions. This is your application of like lecture taught questions, which admittedly is way harder, but you must understand. So let's go through some of the questions after I collect some different solutions. Okay. First. Okay, I'll try those who haven't answered yet. Give everybody a chance. Okay, so Wei Chong, can you try explaining your answer? Your simple iterative solution, and also go through the time and space.
So basically, it will just loop through everything. Then if the index is odd, which is like 0 to 4, then it will add all the values up, then vice versa for the even sum. Then we'll return the tuple of odd sum and even sum.
Yep.
Then the time complexity should be O(n) because it loops through all of it. While for space, it should be O(1) because it only stores 2 things, which is odd sum and even sum.
Yep. Okay. And also another thing to note is like, okay, it creates another tuple, but note that this tuple is a size 2, is a constant tuple. So every time, no matter how big this tuple, input tuple is, this return tuple that is made will always be a constant size. So this part is also constant. Yeah. So constant space, correct. Okay, let's see a simple recursive solution. I wonder if anybody has that. Okay, I haven't seen a recursive solution for this question yet, so we'll put that on hold first. Okay, let's look at a slicing solution. Let's see who provided a slicing solution. All right, okay. Godwin, can you explain this, how your solution works?
Yeah, so I create a list slice using val that first expression. And from there I use sum to find the total sum of that tuple. Then I do the same to generate the sum of the even part, and I create a tuple using both of these sums.
All right, so what's the time and space complexity?
Okay, the time complexity is O(n) because the list slicing itself takes O(n) time. The sum function also takes O(n) time, but since they happen sequentially, it overall still equates to it being O(n) time.
Yeah.
And for the space complexity, it's also O(n) space because the slicing itself creates a new tuple with n number of elements, and then the sum function takes O(n) space. So overall, it's still just O(n) space.
Yep, correct. Okay, we actually had, I got a question, a PM, that asks, can I clarify how space complexity in recursive functions are calculated? So it returns this even rank. So let's look at Isaac's question. Thought process is overall space complexity equals recursion depth plus max new space used at a point in time. But since tuple slicing creates a new tuple and takes over space, the recursion will add space. Oh, right. So let's illustrate this in Python tutor. So he asked about how we calculate time complexity or discretion. Okay. I mean space complexity for recursive functions. And this is not a simple recursive solution. It's not a simple recursive example because it also has this slicing step that happens within the recursive call. So even rank, the recursive version, as a base case, but in its recursive call, it performs tuple indexing, which is O(1), but it also performs slicing to provide the input to the next recursive call. So let's do an example of, let's say, even rank at tub1. So let's create tub1 as I for I in range 1 to 11. Okay, so this is a list tub1. Oh, actually, I should make it a tuple. All right, so this is like a visualization of the recursive call stack. So these will be like deferred calls. So even rank will have, let's say, even rank with the input tuple, then it will call in its recursive calls like to subsequent sub tuples. So each of these will be a deferred operation that holds onto the tuple. And yes, so all right, so Isaac pointed out a good point, because in each step we actually perform tuple slicing. We actually create like a tuple which has a max size of the input size n, and there are n deferred, n divided by 2, but it rounds up to n deferred operations. And that's why the total space complexity should be n times n. Okay, Isaac is correct. So okay, I made a mistake up here. For the simple recursive solution over here, the space complexity should be O(n) squared. Okay, good catch.
Wait, TA. Then the
Yes.
time complexity is wrong, right? Because the space can't be more than the time.
Let me seek a little bit of help. I think, yeah, because this was, oh yeah, this definitely is a time of space. This is definitely a time of n squared. Because this step will be performed n times. So this slicing takes n time, and there definitely will be n divided by 2, which simplifies to n recursive call. So n times n will be n squared, yes. And you want to see a deeper explanation over here, can. So yeah, thanks for pointing that out. I forgot to look thoroughly at each recursive call. So yeah, so this is not that simple for a recursive solution. So this kind of form for recursive functions, where there's a base case but also recursive steps, is not always O(n). You need to be mindful of what extra operations are being taken at each recursive call. So let's say we have some functions where this particular step can take O(n) time, or this particular step that modifies the input may take O(n) time. And also there could be stuff that happens up here also. This could take a variable number of time. So you need to evaluate and see. You need to count at each step. There are also situations where the base case might have like different things that could take different time. So you have to evaluate and count and write an explanation on like what is taking time. Maybe you can point out which steps this particular step is taking O(n) time, and that's happening n times because of the recursive calls. Yeah, okay. Thanks for pointing that out. I missed that. All right. Okay, so for accumulate, let's see, somebody provided a solution using accumulate. Let's see. All right, Junhan. Junhan, can you explain your solution?
Yes, evening. So basically for my answer, first I have all the even numbers and the odd numbers out separately. Then I use the accumulate so that because it's sum, so it's addition, so I have s plus y as my function. So my initial I put it as 0 because I mean 0 plus everything is just the knitting. So afterwards I sum all the even numbers as well as all the odd numbers separately to have my answer. Yes.
Yes. So what's the time and space complexity?
For time, okay, each the one doing the okay, for slicing will be O(n), and the recursive call is also will be O(n), but I'm not so sure if after add up should be O(n) or O(n)3. So I'm not sure about that.
All right. So let's look at the accumulate function. So okay, so take note when you evaluate like time and space complexity in exams. So usually we look like the main function. But if the main function were to call helper functions, we need to evaluate the time complexity of the helper functions too. So first, let's look at accumulate. So accumulate takes in a function that performs like an operation. So the operations we do here are addition. So we know that the operation will always be on. Or here in its recursive step for accumulate, we'll index a sequence that will always be O1. Now over here, okay, we see over here there's an instance of slicing, a sequence slicing. So when we input a tuple to accumulate, it will perform slicing at each recursive step of accumulate. So this will be an on step that repeats n times. So therefore, accumulates time is O n squared. And for space is the same because of what we went through just now. So we know that this step takes on time and this step takes on time. But you realize in Python, because this is okay, because this will happen sequentially. First, Python will evaluate this entire call first. So notice that this is a tuple with two elements, right? One, the result of the first accumulate call, and the second is the result of the second accumulate call. So Python will handle those sequentially. It will evaluate this entire line in full first, and notice that it takes O n squared time. Then once this is evaluated to a value, so let's say at 5, then we will evaluate this. So since all these happen sequentially, we'll add them all together, n plus n plus n squared plus n squared. Overall, the time complexity is O n squared. If you want a visualization of this, you can use Python tutor. So edit the code. One visualize execution. And you run through the execution. You can see we start from the input, which is on, but there will be roughly on divided by 2, which rounds up to on number of deferred operations or recursive calls. And in each recursive call, we have to keep track of like another subtuple that's being created from the slicing. And each tuple has a space complexity of like on. Okay, each tuple takes up a space of bounded by on. So that is n times n times. So time and space is n squared. All right, okay, let's quickly go through question 5. Okay, so can we see your answers for question 5? Okay, this is a tough question. Okay, it's also rather complicated to explain, so I won't put you guys through that explaining it if you all don't want to. Okay, is anybody interested in explaining it before I go through like a visualization of it? Anybody wants to explain their process? You can just raise your hand or just start speaking. I'll give you like 10 seconds. Who wants to explain their solution?
I can explain, but I think that's my answer. So,
All right. So wait, let me look for your answer. Where is it? Okay, yes.
because I went about it logically. So in order for it to move from A to B, if it's only one, you move it directly from the source to the goal. If there's any more than one, you have to move every this above the last one to the subsidiary one, and then move the last one to the goal, then everything back to the middle. So logically,
that's
that's
right.
how it works. But now, if I'm going to ask about time and space, I cannot because I'm not sure how long.
No, it's okay. I also have trouble explaining the time and space complexity of Tower of Hanoi because it's very, very complicated, and that's why we don't even ask. Yeah, yes. But I will show you a visualization of it. So if you want, you can read through it. But let me show you my slides on it. Let's see. All right, so this is the question. All right, so I'll go through like a small guide on how to go about writing recursive solutions. So this actually goes for any question that could come up for that requires you to write a recursive solution. So the processes are usually the same. You think about the trivial basic cases, and then you think about how the next simpler case from the end case. So when you write a recursive solution, right, you need it to be able to solve every case, right? Every end case. So it's very similar to mathematical induction. So if you have learned math, so recursive solutions are basically like that. First, you need to think about the trivial basic cases for what is the most simple case to come out. So like the P1 case. And you have to think about the next simpler case to come out. So that's like the Pn-1 case. So that is required for you to provide a solution for the n case. So let's see here. So over here for Hanoi, we want to solve a problem that has n disks. So that's the problem. The varying problem is solve the Hanoi problem with n disks. So the base case, what is the most trivial case for the Hanoi problem? The Hanoi problem is basically only when it's one disk. So when we only have one disk in the source, we simply just provide the move 1, 3 that moves the disk from the source to the destination position. Yeah, and that is solved. So this is the simplest case, Hanoi 1. Now, you think about the next simpler case, which is the n-1 case. And you have to think about how you relate it to the n case. So when you want to solve the general Hanoi n problem, right, over here, so I colored it like this. So these are the top n-1 stacks, and this is the bottommost stack. So this is n. So let's see. This is the n case. This is the full case we want to solve all the time. So how do we solve this? We basically want our program to move the top n-1s over to the destination. So to solve the we need to move destination, right? Destination, we have to take this stack over to the auxiliary pole like that. Then once we do that, we move everything that's in the auxiliary pole to the destination. So this is our simplified, like higher order thinking of the high level explanation of what Hanoi is actually doing. So this is step 1. Step 1 for the general case. Move the n-1 to the auxiliary pole. Then this is the middle step, step 2. The same thing as all your solutions actually provide is move one disk. So you see, you move only one disk from source to destination. So you input the source, use the source, destination is the original input destination, and auxiliary is the original auxiliary. So notice that for your different calls, we may use different things because over here, look, for the input to destination, we actually set it to aux because why? We are moving the n-1 stacks over to the auxiliary. So this is our destination for step 1. We want to move this n-1 stack over to the auxiliary. So that's why we set auxiliary, the input auxiliary, to destination in this call to Hanoi. to this intermediate call. And then we set the auxiliary, we use the destination, the original input destination as our intermediate auxiliary. Okay, so if you all didn't understand, you can stop me. But basically, this step basically transfers, it performs all the steps, like maybe lots and lots of steps that pushes all of this over to here. And then in step 2, the middle step, we basically simply perform the base case, which is just move the one biggest ring from the source to the destination, which is why we use the original input source as the intermediate source, the original input destination as the intermediate destination, and the original auxiliary pole as the intermediate auxiliary. Then lastly, this is our step 3. Step 3, we already have our n-1 rings over here. We need to move it over to destination. So what do we have available? We have the source, the original input source pole. So what we input to the function is we want to move n-1 rings, the top n-1 rings, which is currently in auxiliary, and we want to move it over to destination. So we set destination as the input destination. This is the original input destination. We move from source auxiliary because this is the intermediate case, right? We are currently, all our n-1 stacks are in the auxiliary pole. So we want to move from auxiliary over to destination. And which auxiliary pole do we have available to use as our intermediate auxiliary? It was the original input source pole over here. This is empty. It allows us to put this in here and move it all the way until this entire step moves everything, the n-1 top rings, from auxiliary to destination. So yeah, and this is a commented solution. So yeah, this is the base case that y'all wrote. So okay, this is in the case of n equals to 0. So this is if there's nothing to move. So this is your actual base case. So this is the trivial case. This is when you only have one ring, which happens during the intermediate calls also. It happens here. You actually do call the base case. So this is the end case. This is the actual code that solves for the general case of any n rings. N can be anything. And these are this is step 1, step 2, and step 3 that I explained in the previous slide. So yeah. With that comes the end of my explanation and the end of the tutorial. So if there's no further questions, you all can leave. Let's see, will our midterms, prac, and finals have any similar to Tower and Hanoi difficulty problems? Okay, I will say no. I will say no because I've done a lot of the past year midterms papers and Tower Hanoi is just like very, very complicated. So you won't have enough time to. Okay, actually, if you can grasp the idea of Tower Hanoi, you could solve it in exams if you have never seen it before. If you think it through the logical way, like what I showed you before. But in my opinion, nothing that difficult has come out for midterms. But you should go through the past year papers. They're in a work bin. They actually are difficult. I would not say they're easy. The midterms are definitely very, very difficult. So you should get some practice and see for yourself like how difficult you find the past year papers. The past 6 years of papers, except for one, has been set by Prof. Tan Tiao Seng. So you should try at least the past 6 years of papers. It definitely will not come out the same thing again, but it builds up your your pattern recognition, so you could apply what you have learned and practice your skills. To confirm how is the box and pointer diagram supposed to look if they are labeled nested tuples within. Like A and B, where do we put B and C? Oh, so Alright, okay, I'll answer the box and pointer diagram question first. Okay, so if there are labeled nested tuples within, what you could do is, let's say, okay, if A is equals to a tuple with BC, okay, somebody asked a question like, how do you write something with BC? Okay, next time when you all ask questions, can you don't direct message me? Can you actually put it in the chat so people can actually see what the questions were? So like when I go through them, people actually understand what I'm talking about. Okay, so Joel asked a question about how to represent a tuple. Let's say B is a tuple with 1, 2, and C is a tuple with 3, 4, and A is a tuple with B and C. How do you draw that box and pointer diagram? You can do it like that. Okay, so let's see what else. Time complexity of the Tower of Hanoi problem. Okay, I actually have an explanation done up by a senior. In the meantime, let's ask Claude what he thinks. Because it's a very complicated this sort of deriving the time and space complexity of this sort of problem, I would say is the 2030 difficulty. I mean 2040. Okay. What is the time and space? So according to according to Claude, it's 2n. According to the senior, this is not done up by me. This is done up by a senior. He came up with this. I'm not sure if it's correct. It's what he gave me. I think this question should be raised to Prof, because we do not have questions that test such complicated functions like Hanoi in exams, in past year papers. Like you can look through the time complexity questions will typically test on a function that you implemented. So like there'll be like a question where, let's say question two is where like the big questions will come out, where there is this problem and you implement, let's say, an iterative solution and a recursive solution, and then you'll be tasked to explain the time complexity of the iterative solution, time and space, and also that of your other recursive solution. So definitely the midterms paper will be set in a way where you are reasonably able to finish within the time limit. Yes. All right, Ashmit, yeah, your explanation should suffice. You do it the math way, which yeah, can. Okay, any other questions? If not, I'll end the meeting soon. What notes would you bring to midterms? Okay, for me, actually everything was allowed, so I just brought everything I had, which was like written notes for every topic. But I would say that it's not very useful because from my experience during midterms, I brought every single notes that I made, and I ended up not looking at it a single time during the midterms because like nothing relevant was there, and I would have known if something relevant would come out because I would know where to look. But like from my experience of doing the entire midterms, like nothing of use was in my notes because everything is very practical. So everything like you've learned was like theory. So you need to apply your skills is mostly through a revision of the past year papers. So you look through the questions and you think from yourself, like, if you were doing that in an exam scenario, what materials or what references would you want to look at? So typically all the different time and space complexity explanations, you should compile all those. So like there for all iterative patterns, all recursive patterns, like all the ON time complexity questions, all the ON recursive space complexity explanations, time and space for each of those different patterns that will come out, you should have an understanding of how to write the explanations for all those. So that could fill a page by itself. You will need to check with a prof what he allows in terms of what you could bring in, because it depends on him every year, like what materials you're allowed to bring in. Is it possible to quickly explain counting change as well as time and space, or is it as difficult as Tower of Hanoi? Okay, counting change is much simpler than Tower of Hanoi. Let's see. I need to look for my week 5. Oh, not this. Oh. What tutorial was that?
I think it's lecture 3. Wait. Yeah. Eh? Yeah, I think it's wait. No, I think lecture 4. Wait.
I remember going through that in a tutorial.
Okay, I'll just look through it. Is there anything I can ask my TA? Or hello, sorry. Wait.
Oh, I think I had it.
Okay.
What do you want to know about counting change?
Like, do you need to like explain like each iteration, like what is left, then the time and space complexity, all this?
Actually, like counting change has a tree-like structure. So with respect to amount and what is it, denominations,
Yeah.
it will split off into a tree for the case where you counting change A minus something. Okay, A minus something and D, and over here is the tree where you do CC A and you go down denominations by 1. So if you only do the time complexity in terms of amount, it will scale to A.
Wait, sorry, where are you drawing it? Because I'm seeing a VS Code. Wait.
Oh shit. Yeah, okay. Yeah, here.
Oh.
So this is your main call, this is your general call of amount equals to A and denominations equals to D. Over here, you split off into one tree for if you minus off the amount, the first amount, X is like the first amount. So this is like the general case. And this is the tree for the case for the second call. The second recursive call of the first call is where you take off the denomination. You basically don't use the first denomination. So basically, what this shows is that if A were to increase by 1, you will have, wait, no, I should put it up here. If you have instead called CC A plus 1 D, you'll definitely get this entire tree. In addition, you get another similarly sized tree. Okay, it'll definitely be smaller, but it is bounded by the size of the other tree. So this is why for tree structures, tree recursion functions, right, it will generally be exponential with respect to the size. So if you actually look at the entire look through the entire thing for amount and denomination, it's actually affected by denomination also, only if denomination is more than A. So you could also say that the time and space complexity of it is like 2 max A D. But just that the question that came up in tutorial is with respect to amount only. So that's why it was 2 to the power of amount. All right, so do you get it?
Okay, so do we need to use words like nesting all this to explain? Like how do we explain in like word form? Like
Right, so your answer was, okay, so if you provide the answer for it to be time complexity 2 to the power amount, right? Then you need to show that there's some sort of exponential thing going on. Like why is the number of steps doubling at each iteration? So it's more of like it splits off here. And you just have to say, basically all you have to say is the number of recursive calls like double for each increment of amount. I think I had the worded answer out here somewhere. What did I write it out? In tutorial. Yeah, I wrote out the explanation. Like if you write that, I think you can get an answer. Yeah, you will get an answer.
Oh,
the number of recursive calls to counting change doubles or increases by a multiplicative factor of 2 for each incremental amount by 1.
Okay, can. Yeah.
Yeah. And same thing for the recursive calls. Like you can look in Python tutor for that call, and you will actually see, like you just look roughly, the size of the recursive call stack is actually ON according to amount. Yeah. Okay, I have another question from Chun Hang. For box and pointer diagram 412, for example, in the inner tuple, will you just draw 1 box or 2, or will you draw 2 boxes? Okay, for that, I'll just draw this. So that is a tuple with 2 elements. First element is 1. Second is another tuple. And that needs to contain 2. Wait, is that? Yeah. Okay, Zhenhan, this is how you draw the box and pointer diagram. You need to reflect the inner tuple as well. Okay, if no further questions, I'll end the tutorial now. No further questions. 5 more seconds. 5, 4, 3. Okay, I'll pause it for now.